Okay, so this is the PhD course on category theory this year. The official title of the course is Brana Poglavia. So selected chapters is računalnička matematika and computational mathematics. Theoria category, but I'll write this part in English. Category theory. So it's officially a course from computational mathematics or computer science, if you like. However, one of the important points, and maybe one of the most important points about category theory, is it's a very... Thank you very much. Sorry, I didn't realize that.
There weren't any batteries down there at the physics department, so I've stolen a remote from the second classroom there.
I don't know if that will work.
I
would say you're going to replace the battery. Yeah. Okay. Thank you very much for doing that.
I need a screwdriver.
We're being recorded at the moment. So apparently we have a screwdriver. Kevin has a screwdriver. So this is going to be an amusing start to the video and to the videos of this lecture. And then we don't know whether the fault, so the problem was with the remote control, I couldn't control the camera. I don't know if that's to do with the battery being, I mean, maybe it wasn't the battery that's the problem anyway. So anyway, we shall find out. Anyway, what I was saying is that one of the beauties and most important points about category theory is it's a very universal subject. It's important in very many areas of mathematics. So it's a sort of unifying topic for many areas of mathematics. And right, thank you very much. So let's see. Well, yes, it was the battery. Excellent, that works. So thank you. So the viewpoint of this course is going to be to consider category theory as a subject in its own right, and throughout emphasize its connections with different areas of mathematics, including računalnička matematika, computational mathematics, but not only računalnička matematika, so also algebra, analysis, discrete mathematics, anyway, all topology, lots of areas of mathematics. Now, I think the background of people in this room is very different. I've had a look down the list of people signed up to the course webpage. To get to know a little bit more about you, I'm going to pass around a sign-up sheet. I would like you to write here your name, the faculty, which maybe for everyone is FMFA, but I'm not completely sure that it is. So, so just in case, stopnia, which for doctoral students is third, and for master's students is second, obviously, but maybe there are even some undergraduates here, we'll see. Then I'm asking you to write your main mathematical areas of interest. So if you're a PhD student, could just be the main subject of your PhD, but the broad area like analysis, algebra, or something like that. And then finally, there's a question, is there any particular category theory, I just write CT topic, that you would like this course to cover? So probably for most of you, the answer will be no, you just want to learn some material, but just in case any of you have any particular desiderata for the course, there's the opportunity to write those desiderata here, and I will take them into consideration. I mean, I may not be able to do it if somebody says infinity toposes or something like that. There is no way I'm going to be able to cover infinity toposes in this course. If you don't know what an infinity topos is, that's good, because if you do know, you shouldn't be taking this course. Anyway, so I shall pass this round and please fill it in as we go along. Okay, so the other thing is, what material will the course cover? Well, category theory is now a very broad area, and but I think something that can be said about it is that almost everybody agrees on what the core, basic, fundamental material in category theory is. That's the material that appeared more or less in Maclean's classic textbook to the subject, which is called Categories for the Working Mathematician, subsequent to which, and also prior to which, there have been many other first textbooks in category theory, all of which cover essentially the same material, not exactly the same material, but essentially the same material. This is the core material of category theory. After that, category theory branches out in many directions, and we might consider some of those directions towards the end of the course. But most of what we're going to be doing is covering the core material that is covered in these textbooks. On the course webpage on Spletner or Chilnitzer, I've given a list of textbooks, including the Maclean one. There are links to a couple of them that you can find online. Actually, the most readable textbook, in my opinion, I haven't given a link to. That's the textbook by Steve Howardy. I think that's the one that best introduces the subject to people that don't have all the background, say, required to read Maclean. Or there's another book I've referenced by Emily Reel called Categories and Context, which I think is a beautiful book. But looking at that recently, I realized that does also need quite a bit of background to look at. So I think the best book to look at is Steve Howardy's book. I did not put a link to that book, that textbook on the webpage, because I think the publicly available versions, which you can find on the web, don't have his blessing to be on the web. Nonetheless, you can find them, but you'll have to find them for yourself.
Could you maybe write the surname?
Steve Howardy. So there's a book, but it's on the course webpage. I think it's called Category Theory. The author is Steve Howardy.
He has a couple of pages about his official courses.
Yes. Okay. So if you look at his at Carnegie Mellon University, and if you look at his web page, you can probably find some more information about the book. But if you simply search for the book, you'll also find a PDF online. So probably more than one PDF. So the course is going to be like a normal mathematical course. We'll go through definitions, theorems, and so on. But one of the main points of the course is that category theory, as I've already mentioned, touches with very many areas of mathematics. And so because of that, an important part of the course is going to be considering examples from different areas of mathematics throughout the lectures. So there are going to be lots and lots of examples appearing in the lectures. Now, there's a slight problem with this, in that it's almost certainly the case that not everyone in the room knows all the background areas that I'm going to use as a source for examples. But you shouldn't worry about that. So what is important is that you understand sufficiently many of the examples. There will be, for every person, there will probably be some examples outside your own knowledge, but those will be different examples for different people. So what you need to do is understand to the best of your abilities the examples from areas that you already know about. I'm not going to be teaching you the other areas of mathematics from which I'm taking the examples, but as long as you understand the examples from the areas you already know about, and from the examples from areas you don't know about, well, you can't understand them fully, but nonetheless, just seeing them will hopefully give you some sort of impressionistic appreciation of what category theory is doing in that case. Okay, are there any questions about that? Right, so then I have a question for you. How many of you know the definition, the mathematical definition of a category sufficiently well that without any textbook to refer to, you would be able to write the definition on the whiteboard from without looking at any other material? So, okay, so if it's like that, then the answer is no. If you're not completely sure, this is do you know it well enough that you can? Okay, so it's about 50-50, maybe not even quite 50%. So some of you know definition of a category. I actually know a few of you in the room, and I know a few of you know even quite a lot of category theory. So this course is not going to assume any prior knowledge of category theory. So for those of you who know some or even quite a lot of category theory, the beginnings of the course are going to be quite basic. There's no avoiding that. I mean, it's a course to cover the material of category theory, and we're going to start at the beginning. Hopefully there will be something of interest for all of you as we go along in any case. Okay, so what I'm going to begin with is getting to the stage that you would all be able to stick your hands up saying, yes, I know the definition of a category, because I've learned it. So that's what the first thing we're going to do is the definition of a category. And then most of the lecture is going to be just looking at examples of categories and some of their properties, and seeing how such examples arise in many areas of mathematics, and such a general structure that examples can be found everywhere. So what is a category? Well, it's a mathematical structure, just like a group is a mathematical structure, or a topological space is a mathematical structure. A category is a mathematical structure. So I'm defining a category here. There are different schools for how one represents category. I come from the school that's a general category is represented by a curly letter. So this is the curly capital C. I'm not very good at curly letters, but this little loop means it's a curly letter. So in LaTeX, this would be \math. Oh, I'm just mathcal. Yeah. Calligraphic. So it's given by some data that defines the structure. So categories, you may have seen pictures, they kind of look a bit like graphs. You have some dots and some arrows. So they look a bit like directed graphs, and indeed, in a sense, they are directed graphs. You have the dots are called objects, and the arrows are called morphisms. But the most important difference you have with a directed graph is there's an operation of composition of morphisms. So if you have two arrows in a line, two in a sequence, then you can compose those two morphisms to get a single composite arrow. Those two morphisms together give you a single composite arrow that represents the composition of those two arrows. That's the sort of picture you see. The mathematical definition formalizes what we would expect from this sort of thing, this sort of structure. So we first have, like with a graph, in the graph you have a set of vertices. In the category we have a collection. I could use the word set, but there's a reason that I'm not using the word set, which I'll come to. So we have a collection, which I'll put these bars by the side of C to represent this, of things called in a graph, the nodes are called nodes or vertices. In a category, they're called objects. So we have a collection of objects, and for every pair of objects, so these are objects of the category C, we have another collection, which we write as curly C X, Y, which we think of as the collection of these arrows from X to Y. And in category theory, the arrows are sometimes called arrows, they're sometimes called maps, and they're most normally called morphisms. So we have whereas a graph has a collection of edges between any two nodes, a category has a collection of morphisms from X to Y. Now, the collection of morphisms is required to satisfy some conditions. For every object, there's a special morphism that from that object to itself. Such morphisms are called endomorphisms. A morphism from an object to itself is called an endomorphism. And this special one is called the identity morphism. So for every object X, there is a special, well, let's say we have a special morphism which we call 1 sub X. This is a morphism from X to itself, and this is called the identity morphism. X. Instead of writing 1x is a morphism, belongs to the collection of morphisms from X to X, one tends to use the simpler notation like this. So this just means this is equivalent to this statement: 1x belongs to the set of morphisms, the collection of morphisms from X to X. Okay. Let's just connect those two. This is the way we normally write it. So we have an identity morphism on any object, and the next condition is that we have this operation of composition of morphisms that I've already mentioned. So so the composition is going to work whenever we have a morphism F belonging to the collection from X to Y, and a morphism G belonging to a collection from Y to Z. So then we've matched the codomain of the first morphism with the domain of the second morphism. We had from X to Y and from Y to Z. They run in a sequence, and we can compose those two to get a composite morphism from X to Z. So using this notation, so for any morphism F from X to Y, and for any morphism G from Y to Z, I'm already using our convenient shorthand notation here. We have a distinguished composite morphism written G. So sometimes one just writes G adjacent to F with no symbol in between. Sometimes one uses just a dot. I'm using the old notation from MacLean, like the composition notation, a small circle. So you write G composed with F, and this is, oh, that's right, we have a composite morphism. It's a morphism from X to Z that we think of as being formed as a composition of G and F. So X, G composed with F, G composed with X, G composed with F goes from X to Z. And so this is the data you need to give. If you're giving a category, you need to specify this. You need to specify its collection of objects, its collection of morphisms, what its identity morphisms are, and what its composition operation is. That's what. So you can view the composition is a function that maps a pair GF to G composed with that takes the product. So G was from Y to Z. X to Y, get in the end map from X to Z. You can view compositions of function like this. It's actually a family of functions, one such function for every triple of objects X, Y, and Z. Okay, and this data is required to satisfy some conditions which are very natural. The idea is we kind of think of an identity function as doing nothing and composite as doing composition as kind of a single morphism that represents doing F first and then doing G. And so these are required to satisfy some laws, which is that if you compose any map, let's put a Y there. If you compose any map with an identity, either on the left or the right, you get the map back itself. So identity morphisms don't do anything. Composition of identity morphisms don't do anything. So this is for any map F from X to Y. And secondly, composition is associative. So if you compose F with the result of composing G with H, oh, sorry, it doesn't matter, it's completely right what I've written, but I'm going to just do it the other way around. You compose H with any map with the composition of G with F, then that's the same thing as first composing H with G and then composing with F. And this is true whenever these compositions make sense. So to form these compositions, we need to have F going from X to Y and G going from Y to Z and H going from Z to some other object, say W. So this is for any, so whenever the composition of the three things makes sense. So for any X from F from X to Y, G from Y to Z, and H from Z to W. Because we have this, so sorry, these are called the identity laws. These are called this is the associative law. These identity laws, because there are two of them, one for the left and one for the right. That's why it's laws. Here we have the associative law. And because we have the associative law, it makes sense if you have any long composition, it doesn't matter how you bracket it. So you tend to omit brackets and you just write the whole thing in a long sequence. So I've been using these, I already said it, but just to say more, the maps, the elements of this object, which is called the HOM object from X to Y, the HOMs from X to Y, you sometimes call them. They're also called morphisms. Well, they're called morphisms. They're also called maps, arrows, HOMs, various lots of words that people use for that. I'll tend to use morphism or map, probably. Okay, so that's the definition of a category. And what I now want to do is consider most of the lecture, a lot of examples of categories and look at some of the structure that comes out from viewing them as a category. And we're going to start off. So the next section is going to be about examples, and it's going to last a long time. So we're going to look at lots and lots of examples. But the first example is, in many senses, the most important category of all. It's fundamental to a lot of constructions of other categories. And this is the category called set. And to underline it, so in most textbooks, this is written in bold. So the underlining means bold. Some people like to use sans serif font instead. Anyway, it doesn't really matter. I'm just going to write. So curly categories are sort of like categories given abstractly. So this is an arbitrary category needs to satisfy these axioms. But I'm going to give names and underline particular examples of categories. So the category set is the category. So this is normally just called the category of sets. When we refer to it as the category of sets, And what that means when one's talking about it is the category whose objects are sets. That doesn't actually tell us everything about the category because we haven't said what the morphisms are. And so in this case, the morphisms are going to be functions between sets. But still, one doesn't want to, when talking about it, talk about the category of sets and functions all the time, because that would be rather complicated, a convoluted expression to use. So it's just referred to as the category of sets. So if we want to define it mathematically, we need to specify what the objects are. Well, I've already told you. The objects are sets. Okay, so we know what a set is. You know, if you do algebra, you know what groups are. So a group is a set with an operation and an identity satisfying some laws. So you know what a set is. Here an object is just a set with no other data. So the morphisms. So we need to define what the POM collection, the collection of morphisms is from an object X to an object Y. So in this case, the objects are sets because we've. Right, let's be even a bit more formal here. So the objects, the collection of objects, will define this to be, so this colon equals is a defining equality, define this to be the collection of all sets. So given two sets X and Y, the POM collection is the collection of all functions all set theoretic functions from X to Y. The identities, well, of course, on any set you have an identity function that takes an element of that set as its argument and gives back the same element of the set. So 1x is defined to, the identity on X is defined to be the identity function that takes an element little x in the set X and gives us back the same element X. So this is a function from the set capital X to itself. So this is going to be my notation for defining functions in this course using the maps2 notation. So we take an element little x, we map it to itself, and this gives us a function from X to itself. Okay. And composition, as hopefully everyone taking this course knows, there is a standard operation of function composition, and that's what the composition is. So given morphisms F from X to Y, and G from Y to Z, so here X, Y, Z are sets because we're in the category of sets. We've got two morphisms with the codomain of the first is the domain of the second. The composition so we define composition G composed with F is just defined to be function composition, which is the function that takes an element little x from the set X and maps it to the result of applying G to the result of applying F to X. With the usual notion of function composition. And one verifies, and I'm not going to prove this kind of thing, I mean, this is like basic mathematics, that identity function and function composition together satisfy the identity laws and the associative law. Okay. But there is a more important remark to make about this category. So I said at the start, categories are just mathematical structures. And here we're defining the kind of mathematical structure that we're looking at. So in a similar way to groups are a structure, so a group is a set together with an operation and an identity satisfying some properties. topological spaces as mathematical structures, and so on. There's a slight issue here in that here we have a category, so it's a structure, but the collection of objects is the collection of all sets. That's a very, very large thing. In particular, you know a bit of basic set theory by Russell's paradox, there is no set of all sets. So this is why in the notion of category, I was using the kind of the rather informal word collection here, rather than the word set. We don't want to say it's a set of objects, because that wouldn't be the case, but that would rule out the category of sets. In this case, for those who know some set theory, the collection of all sets is a proper class. But you also don't want to be so restrictive in the notion of category that you restrict to sets and classes. There are various sort of levels at which one might want to make sense of categories. And one of the slight issues with getting used to category theory to begin with at the beginning is that we're dealing with mathematical structures, but a lot of our examples of these mathematical structures are going to be very, very large things. So unlike a group, which is a set to begin with, and it's like a manageable thing to have at hand, here we're dealing with a mathematical structure that is very large. If we look at the morphisms, however, the collection of all functions from, we've got a fixed set x and a fixed set y here. There is only a set of, between only two sets x and y, there's only a set of functions between x and y. In this case, we can improve this to the set of all functions from x to y. So I'm going to introduce you to some terminology here. We say that a category C is locally small if every Hom collection is a set. If for every x and y, the collection of maps from x to y is a set. We say that C is small if it is locally small and moreover, furthermore, the collection of objects is also a set. So using this terminology, the category of sets, our most important example, leading example of a category is locally small, but not small. Set is locally small, but not small. Right, before I rub this board off, I realised I didn't introduce some terminology, though I've been using it. So let me just do that briefly. So given a map F from X to Y, so morphism F from X to Y, an element F of the Hom collection C of X, Y, we say that so X is called the domain of F, just like the domain of a function, and Y is the codomain of the function, of the morphism. And one of the things about categories is this is a really motivating example for a category. Identities are given by function identities. Composition in the category is given by function composition. And a lot of the terminology of category theory is essentially motivated from that kind of example, where one thinks of morphisms as kinds of functions, and the idea is one's considering some kind of transformation from one object to another, and the object of composition is giving us a way of composing those operations. And a lot of the terminology, such as composition, identities, domain, codomain, and so on, are inherited from the terminology associated with functions. And we're now going to consider some more examples of categories. And for the next few examples, they're all going to share the property that, like with the category of set, the morphisms are essentially functions, but are functions of one kind or another, and the composition the identities are identity functions, and the composition operation is functional composition. And I'm going to go through these quite fast, and then we'll have the break. I'm going to have 3 such examples. So I should say there are going to be some notes which I'll put online. So this is essentially what I'm following in the lecture. They're handwritten. They're handwritten notes. In some cases, there might be just a little bit more detail in the notes because I won't have. But I'll let you know when that is. So you're welcome to and encouraged to take your own notes in the lecture, but there will be notes put online as well. Okay, so I want to consider three other, and there are so many more examples I could consider, but one has to. This is I thought sufficient variety for this first lecture. These 3 next examples. After this, we're going to move to examples of a different kind entirely, and that's going to be perhaps more interesting. But the 3 examples I want to consider are now. Top category referred to as the category of topological spaces. And again, in saying that, we don't say what the morphisms are, that one wouldn't want to have too long a phrase to refer to it, but the morphisms in this case are continuous functions. So now we get into the stage that it does not matter if you understand every example, but just out of interest, how many people here know the definition of a topological space, a general topological space? Okay, good. So that's all right, that's great. And I'm not going to define things from other areas of mathematics, I'm not going to define, but it's the sort of thing, if you didn't know that, it's not a disaster as long as you know sufficiently many of the examples. So here, the objects are, so collection of objects is the collection, again, it's not a set, collection of all topological spaces. And morphisms are that actually I think in my, let's use different symbols. So an object is now a topological space, so we're considering the collection of morphisms from the topological space S to the topological space T, and this is just going to be the set of all continuous functions from S to T. And I'm not going to write it down, but identities are again identity functions, which are of course continuous, and composition is again function composition, which is okay, because if you compose 2 continuous functions, you get back a continuous function. Continuous functions are closer under composition. And of course, the identity laws and associativity law are inherited as a true now because they were true of general function composition in the first place. And again, this is this is locally small, but not small. That's one example. Next example is the category of groups, GRP. And appropriate notions of maps between groups. So what's the normal notion of a map, functional map that one has between groups? Of course, a homomorphism. So now one again just refers to the category of groups, but the morphisms in this case are homomorphisms. Almost, having said this, I almost don't need to do the rest of the definition, but I will do it in this case, and I won't do it in the, in fact, I won't do it in this case. You can look at the notes. But anyway, the objects are the collection of all groups, and the hom collection of group from one group G to another group H is the set of all group homomorphisms from G to H, or simply homomorphisms from G to H. And again, this is a locally small category because there are only there's a set of homomorphisms between it. If you're given two groups, there's a set of homomorphisms between them, but it's not a small category because there's no set of all groups. Groups can be arbitrarily large, set theoretically. And lastly, the last of these kinds of examples, vect sub K is going to be a category of vector spaces over K, where K is a field. So given a field, you have the notion of a vector space over the field, and the collection, considering the collection of all such vector spaces. So this is a field here, as the collection of objects. And again, we would normally just refer to this as the category of vector spaces and assume that we know which K we're talking about from the context of the discussion. And we wouldn't refer to what the morphisms are, because when you say the category of vector spaces, everybody knows what the morphisms are. What do you think the morphisms are between two vector spaces?
Linear maps.
Linear maps, very good. Or linear transformations, as they're often called. And linear transformations. And indeed, the identity is a linear transformation. The composition of linear transformations is a linear transformation. So everything works out, and we again get a locally small but not small category where the morphisms are special kinds of functions. And it's now basically 11 o'clock, so we're going to have an almost 15-minute break and start again punctually at 11:15. Okay, so let me pause the recording. Okay, so we've seen several examples of categories, and in all cases they were locally small but not small categories whose morphisms were certain kinds of functions, and the composition operation was function composition. I'm now going to consider examples that are of a very different nature. So the first such example is the category rel, which is referred to as the category of relations. If you talk about the category of relations, you mean this category rel. But this use of terminology is different from the previous uses of terminology, in that in this category, the relations are the morphisms, not the objects. So we talk about the category of relations, but it's the category whose morphisms are relations. So this is the category objects whose objects are sets. So using the sort of way I was writing things before, we put the objects first, which is the category of sets, and the morphisms are relations between sets, binary relations between sets. So I'm going to define this in a bit more detail rather than being quite as fast about it as with the other examples. So the objects, that's easy. It's just, again, the collection of objects is a collection of proper class, if you like, of all sets. The morphisms are where things get interesting. So the set of morphisms, it is going to be a set, so it's again going to be a locally small category between a set X and, well, from a set X to a set Y is going to be defined to be the set of all binary relations between X and Y. So the defined to be the set of all binary, that alone write that down, relations. We think of it going from X to Y, but you think about relations between two things. So relations between X and Y. So what is a relation between X and Y? Well, this is something I guess everybody knows, but I don't quite know the terminology in Slovene in this case. So, but there are different ways of defining it. So one way of viewing a relation between X and Y is a subset of the product X times Y. So namely, you're pairing things in X with things in Y, and a pair of elements, little x and little y, are in the relation if and only if they're in the subset. That's one way of defining a relation. An equivalent way, I mean, an alternative, but it's equivalent, which is the one I'm going to use, is a relation is, so between X and Y, a function are, let's say, from the product X times Y to truth values, to true and false. So this function, you give it a pair, little x and little y, and it'll tell you true if that pair of things is in the relation, and false if that pair of things is not in the relation. I'm tempted to use the other board here, so so you can view a relation between finite sets as what's called a bipartite graph between the two sets. A bipartite graph is a graph where the vertices are split into two. The one's here on the left, and here I'm going to draw a relation between the 3-element set and 4-element set. And the relation connects, so because it's a category, we have a direction to it, even if the idea of a relation doesn't so much have a direction. But I'm going to give you a relation from this set here, the 3-element set, to the 4-element set. So this is the one where this element is related to these 2 elements. This one is related to these 2 elements. And this one and this one are just not related to, hang on. I didn't want to draw this. I do want to have the same example as in my notes so I don't make a mistake when we do something with it. So I actually want it to be like that. Obviously. Oh my God, what am I doing? No, no, this was right. It was right before. Almost. I'm sorry, it's literally an issue of just making sure I'm copying the picture. Anyway, you've now seen about 3 examples of relations between these two sets. But anyway, you see which pairs are in the set, namely those that are connected by lines. And what's interesting about this example is that the notion of composition is not function composition. So the identities these can be viewed as function identities. So the identities are that the identity on a set X is, again, the identity function from X to itself. We want it as a relation, but we have the notion of the graph of a function, which is always a relation between the domain and the codomain. So the graph of the identity function X maps to X. Or in other words, this is the function that X and Y, so a pair of elements from X and itself, from the set X, capital X and itself, map to true if X equals Y and false otherwise. Composition is the interesting operation. So given relation R considered as a morphism from X to Y, so that's a relation from X to Y, and S, relation S from the set Y to the set Z. Composition S composed with R, which we want to be a morphism from X to Z, is given by the relational composition which is often written as R semicolon S. This is a standard notation for relation composition. Doesn't matter if you haven't seen that notation before. I'm going to define it now. So we want to define this relation composition R composed with S. It's going to be a relation. It wants to compose this as going to be a relation between X and Z. So we want to say, we want to define when a pair little x of an element from the set X and little z an element from the set Z, when these are related by the relation composition R followed by S. And this is defined to be the case if and only if there exists some intermediate step element Y such that little x is related by R to Y and little y is related by S to Z. So this is, there exists a y, little y belonging to the set Y such that X is related by R to Y and Y is related by S to Z. In the case of finite sets, where we can view relations as bipartite graphs, we go to the other board. There's a very natural pictorial understanding of relation composition. So this is one relation here, let's call that R, and here's another relation. Again, let's go back to a 3-element set. Here's another relation to a 3-element set from this set. So this is going, so here we're going to relate these two pairs, these two, and these ones. So I might write, this is a set here, but let's just write 3 because it's a 3-element set. So we've got a morphism. R is a morphism in the category of relations from a 3-element set to a 4-element set. And here we've got S is a relation from back from 4 to 3. And the composite relation, how do you understand composing these relations? Well, we want the composite relation is going to relate X. So here we've got X, Y, and Z. It's going to relate X, the 3-element set, to Z, which is the 3-element set, again. And you can view the composite relation as you relate 2 points, if and only if there's a path from one point to the other, I mean, a direct path that goes direct from X to Y to Z. You're not allowed to go around. I don't know if it makes a difference, but anyway, just in case it does. But anyway, a direct path, there's a path going from X to Y to Z that leads us to those points. So here we can see that this point is connected to this point by this path here. It's connected to the top point via this path there. The middle is not connected to the middle point. The two middle points are actually not connected to anything. And this point, the two top point, well, anyway, you get this picture. Let's rather than trying to speak a picture that's easily drawn, let's draw it. So that's the picture. So that's an example of relation composition, but it is not function composition. And nonetheless, this gives us a category because the identity morphism and relation composition is associative, and with the identity morphism, it satisfies the identity laws. Again, it's a locally small but not small category because the collection of objects is a proper class. Okay, so that's one very different example. I'm now going to consider some examples of small categories. And kind of the underlying message is that so far many, if you like, settings for mathematics, so set theory, topology, group theory, linear algebra, so you've got relational algebra, if you like. There's this kind of category that is the setting for those subjects. We've got categories, the various categories, each of which is associated to one of those subjects. But now we're going to look instead as individual mathematical structures as forming examples of categories. And a really nice example of this is individual groups. So let G be a group. So what is a group? Well, it has a multiplication and an identity, and that specifies the group. So let G with the multiplication and an identity be a group. Then for any group G, we can form G underline, which is the group G as a category. We can form a category from the group G. And this is a very minimal kind of category in that the objects don't play any important role, because there's actually only going to be just one object. So just one object, which we'll call star. It's kind of star is going to be our symbol for a sort of anonymous thing. Or alternatively, you can define the set of objects of G to be the singleton star collection of objects. So the place where the group structure goes is into the morphisms. So we need to define what the set of morphisms is between what the collection of morphisms is between any pair of objects. But there's only one pair of objects possible because we've only got one object. So the collection of morphisms from star to star, and we simply define that to be G. The set, so the collection of morphisms is the group G. So elements of the group, the morphisms are elements of the group. And the point is that the group structure gives us our identities and our composition. So the identity of the group is the identity morphism, and the multiplication in the group is composition in the category. So, so identities are that the identity morphism of the group of the only object star is E, the group identity, and composition so if we're given a morphism X from star to itself and a morphism Y from star to itself, then we define Y composed with X to simply be Y multiplied by X in the group. And this satisfies the identity laws because the identity in a group satisfies the identity laws, and it satisfies the associative law because group multiplication is associative in the usual algebraic sense. And having made those observations, one sees that actually to make this construction, to get a category, we didn't use the full power of this algebraic structure being a group. All we used was that we had an identity and that the multiplication was associative. And in fact, there's a notion of algebraic structure that has exactly those axioms and no more, and that's called a monoid. I'm not going to write it down, but so these are the sorts of things you can, as I say, you don't need to understand every example, but you can also look up definitions or even infer them. And I've already given it, I've already spoken it basically, but so in fact, the same construction works to define a category. So it works more generally because monoids properly generalized groups, a category M associated to any monoid M. Well, again, you have a multiplication and an identity. So this is a small category. Clearly, it's locally small because the Hom collection is a set, because the group was originally a set. And obviously, the collection of morphisms of objects is small because it's a singleton. So this is actually a small category. Again, identities in composition are not function identities and function composition. They're now it's now the identity and multiplication in the group. So the interesting thing about this is there's a way of turning it around as well. So here we've constructed a group and, well, sorry, constructed a category from a group and more generally from a monoid. In fact, we can, given the category, we can get back the group or the monoid in the case. And in fact, it's such a trivial step between the two things that you can almost take this as a definition. And there's a kind of, people call this categorification, where one derives mathematical structures from categorical versions of them that are equivalent. So I'm going to write this down in the case of a monoid. So I call this in the notes categorification. I won't write that long word on the board, but you can find it in the notes. So one can consider that one is using, if one, rather than using the algebraic definitions, if one already knows the notion of a category, there's a very simple definition one can give of a monoid. A monoid is simply a category with a single object. A monoid is the same thing basically as category with one object. So monoids, so categories in a vast sense, properly generalized monoids. And we're going to see later, we can do the same with group. The group, if we want to define the notion of group, we need to have the notion of an isomorphism in a category. So the group is just the same thing, essentially. It's a category with one object in which every object is an isomorphism. So
probably missing one.
With, oh yes, I am missing with one object, with exactly one object. Well, in fact, let me just put that down now. So group, I haven't told you what an isomorphism in the category is. Probably most of you know that already. But anyway, a group is exactly the same thing as a category with one object in which every morphism is an isomorphism. But we're going to do isomorphisms in a moment. Anyway, the point is that beloved mathematical structures arise as special instances of categories. And at the moment, it's just a trivial observation, but it does actually have some mathematical mileage to it. which we'll see later in the course. So, last collection of examples is going to be similar. We're going to turn a different mathematical structure into a category, and that's partially ordered set. We're going to see that partially ordered sets are also any partially ordered set can be turned into a category, and basically partially ordered sets are the same thing as particular kinds of categories. So remember, a partially ordered set is a set together with a partial order on it. There's a strict version and a non-strict version. I'm writing less than or equals. It's a non-strict version which satisfies the reflexivity axiom that everything is less than or equal to itself. So be a set with a partial order, or a partial order, or a poset. This stands for partially ordered set. Again, we're going to define a category P underlined, which is the poset P as a category. And the definition of this is almost dual to how we define groups as a category, in that with groups, the objects were uninteresting and everything of interest was in the morphisms, whereas with partial orders, the morphisms are going to be uninteresting. Well, the only interesting thing is whether there exists an morphism or not, but all the information is going to be in the objects and the existence of a morphism. So how it works is the objects are just the objects of the category P are just defined to be the set P, so the elements of the partial order, and the morphisms are that if so we want to define what the set of morphisms or the collection of morphisms is between an object little x and an object little y. So here, little x is an element of the partially ordered set and little y is an element of the partially ordered set. And this set is going to be, the idea is you have at most one morphism between any two objects. The morphism exists if and only if x is less than or equal to y in the partial order. So the existence of the morphism is basically saying, yes, x is below y. It's just giving the statement that x is below y. So we're going to have a single morphism, which in the notes I write star because I'm using my own notation for anonymity, star comma little x comma y for that morphism. So we want a singleton set. But I don't really like that notation actually. So I'm just going to write this. And the point is, let's put quotes around it. So we think of this as a name, but basically the point is this is a singleton set. It doesn't matter what we call the element in it, really. We just need some name to give the element of it. But the point is that it is a singleton set. It has an element in the case that x is less than or equal to y, and in the case that x is not less than or equal to y. The correct English to put here in the cases definition is otherwise, by the way. I often see from Slovenes else, but you can't write else here. You need to write pasica, but you need to write otherwise. Anyway, so in the case that x is not less than or equal to y, the collection of morphisms is empty. I don't need to say what the identity morphism is. It's the unique thing it can be. I also don't need to tell you what the composition is. It's again the unique thing it can be. Composition is well defined because of the transitivity axiom of a partial order. That's why composition works. So I won't define the identities and composition. I will again make the comment that for this construction from a poset to a category to work, we actually didn't need all the axioms of a poset. We never used the anti-symmetry axiom, which is the axiom that says if x is less than or equal to y and y is less than or equal to x, then x equals y. That axiom is never used. There's a more general notion of an order called sometimes a quasi-order, or quasi, some people say, or a pre-order. I prefer the term pre-order, in which you don't have that antisymmetry axiom. You just have the reflexivity and transitivity axiom of an order. And this construction works for that. So more generally, we can define the category P for any pre-order. So pre-order is again a set with a relation, but it just only satisfies reflexivity and transitivity, not necessarily antisymmetry. And once again, this is again there's such a tight connection between the category we've constructed and the original post set that one could say, well, again, we can essentially derive pre-orders and partial orders as the very notions themselves are special cases of categories. And so the categorification in this case is that the notion of pre-order is the same thing as a category, or let's just say category with at most one morphism in every Hom-set. And a partial order, so a post-set, is the same thing as a pre-order that satisfies the antisymmetry property, but again, that makes sense, and one can make category theoretic sense of that, that the antisymmetry property can be expressed as the only isomorphisms are identities. So only the identity maps are isomorphisms. So I still haven't said what an isomorphism is, but we're going to come to that in just a moment. So a poset is a category with at most one morphism in every Hom-set, and the only isomorphisms are identities. Just put a D in there, are the identities. Right, so I've used the word isomorphism twice. So I want to now move away from examples and go to considering a couple of things we can use the category. So a category so far is just a very general structure. All we've got is we've got these notions of, we've got the objects, we've got the morphisms between them. We've got the composition, and it satisfies some very basic laws. To do interesting mathematics, one needs to put more structure on that. And we're going to do that, a lot of that later in the course. But one can get a certain distance just with the properties we've got so far. So in any category, we have some interesting notions that can be defined just in terms of the basic structure of the category. Isomorphisms are one such notion. Two other such notions are what are called monomorphisms and epimorphisms. So let me define those. So, a morphism in a category is an isomorphism. I think I didn't move the camera. Isomorphism, if it's, well, in mathematics, one's used to the idea isomorphisms have inverses. So the point is, the axioms of a category are enough to express the notion of having an inverse. So an isomorphism is simply a morphism that has an inverse. But if there exists a morphism from y to x that acts as an inverse to y, what being an inverse means is it means it's both a left and right inverse and a composition giving back the identity. So if there exists a map from x to y, sorry, from y to x, going back from y to x, so I'm going to write also maps the other way around when appropriate. We'll call, I mean, here I could say a map G satisfying these properties, but in practice we'll call this map f to the -1. So such that if we compare, it acts as both a left inverse and a right inverse to f. So if we compose f to the -1 with f, well, that gives us a mapping from x to itself. So this is required to be the identity on x, and s dot t dot means such that, and if we compose f to the -1 on the right, that gives us a map from y to y, and that needs to be the identity on y. There are some basic exercises in the notes, including the following, and I recommend this exercise. It's very straightforward, but if I would like you to all try it, and if you struggle with this, please come and ask me. But this is hopefully going to be okay for all of you. I mean, anyway, which is prove that if f is an isomorphism, then that determines f to the -1 uniquely. So there is a unique f to the -1 that satisfies these two properties. Okay, so the inverses are unique. So while I'm defining notions of morphism, I also want to take the opportunity to define a monomorphism. Sorry. Let's just keep with f, so that f is a monomorphism if a slightly more complicated property holds, which I'm just going to write down and then motivate it afterwards. So this is, well, let's keep, this is again f from x to y. It's a monomorphism if for all parallel pairs of maps into x and y. So I'm just going to simply write it like this. So for all, let's call these maps x and y. And what I'm really saying here is for all objects z, and for all morphisms little x from z to x, and for all morphisms little y from z to x. I'm just writing as little as possible on the board to say that. So for all parallel pairs of maps from an object z into x, we have the implication that if f composed with x, which is a map from z to y, equals f composed with y, then x equals y. And my motivation, the motivation I'm going to give for this, is that if we view f as a function, and we're applying the function to arguments, this is a definition of this is one way of defining what it means for a function to be injective. Okay? So this is a sort of category theoretic generalization of the notion that a function is injective. But the point is, it makes sense in any category. Both these properties make sense in any category. Given a morphism, you can ask, is the morphism an isomorphism? If so, what is its uniquely determined inverse? Is the morphism a monomorphism? So what I want to end with is classifying the morphisms. We've got all these examples. What are the isomorphisms in the, and what are the monomorphisms in the categories, in the example categories we've looked at? So the categories were set, and the isomorphisms are, well, what do you think the isomorphisms are in category of sets?
Bijective function.
Bijective functions, or so isomorphisms are going to be in blue here. They're bijective functions, or also another word known as bijections. And what do you think the monomorphisms are going to be? Injective functions or injections. Let's put monomorphisms in green. I've left enough space for the. Okay, the next example was top. So any idea? Does anyone have an idea what the? Very good. So the isomorphisms are going to be the homeomorphisms. And let me just tell you, the monomorphisms are the injective continuous functions. Which is different from embeddings. It's a weaker property than being an embedding. Okay, so it's not the topological embeddings. I mean, every topological embedding is an injective continuous function, but there are injective continuous functions that are not embeddings. But these are the monomorphisms. So in group, any idea?
Isomorphisms.
Yeah, group isomorphisms. So it's what it says, which is the same thing as bijective homomorphisms. So let's, since, and again, monos are the injective homomorphisms. Which in this case is the same thing as a group embedding. Vector spaces. We have the linear isomorphisms and linear injective functions. So injective linear transformations. In a group G. So what are the isomorphisms in a group G?
There's only one.
Nope. All the maps. So very good. There's only one object, but the G group. And an exercise is that every isomorphism is a monomorphism. I didn't write that down, it's in the notes, but don't have time to write everything on the board. That's an exercise. So again, what are the injections? What are the monomorphisms? Well, again, they're all maps. Finally, P, a poset. I've already told you the only isomorphisms in a poset, you need a map in both directions. And because a map in both directions says that x is less than equal to y and y is less than equal to x, in a poset you have the antisymmetry axiom, so x equals y, and then it's the only map from x to itself, and that's necessarily the identity, and that's an identities are always isomorphisms. That's another obvious thing because they're their own inverse. So in this case, the isomorphisms are just the identities. Any idea what the monomorphisms in a poset are?
All the maps.
All the maps, very good. So this, when you look at this, because there's a most one map here, the equality is trivially true. So the equality that needs to always hold is trivially true because you've got two elements x and y, they're necessarily the same because there's at most one map. So here we have all the maps. I've missed out an example. I mean, I didn't mention monoids and preorders, but forget that. I've missed out the category of realm. So what I want to end with is I'm going to try to do this every week. I hope I'll find a good one every week. I think this is quite a good one. What I'm going to call your weekly puzzle. The weekly puzzle here is, I mean, you can do what are the isomorphisms in the category realm of relations. That's quite straightforward. But the real puzzle is what are the monomorphisms in the category realm. By what they are, I want a characterization of them in non-category theoretic terms, so not using composition, but a direct combinatorial, as you like, characterization of the monomorphisms. And two leading up questions to this are, is there a monomorphism? One often abbreviates monomorphism to mono and isomorphism to iso, so I'm going to abbreviate. Is there a monomorphism from 2 to 1? So namely from a 2-element set to a 1-element set in REL. And once you've answered that, is there a monomorphism from 3 to 2? A 3-element set to a 2-element set in REL. I would start on this first question. This is not too hard because there are only 4 relations from 2 to 1 in the category of REL. And when you get to the second question, there are 64 relations from 3 to 2. So it's not going to be very easy to consider them all on a case-by-case basis. So at that point, we might start to think about this question, and that will hopefully help you to answer that question. Anyway, good. So that's everything for today. I'm going to stop the recording. So Blanche, thank you very much for your attendance. If you have a question,